It's a pleasure to have our second speaker here now, Fabrice Baudoin, who is a professor at the University of Connecticut. Fabrice was a student of Marc Yor and Huyen Pham. Again, not hopefully too many years ago, because it was the same time I was a student, and also worked with David Nouillard. He works on stochastic analysis, rough path analysis, and sub-Riemannian geometry. And today he's going to talk about logarithmic Sobolev inequalities and how they fit into all of the things that we love. Take it away, Fabrice.
Okay, thank you, Todd. So thank you to the organizer for this very nice workshop. So I was asked to give an overview talk, survey talk on log-Sobolev inequality. So I will not present anything new in the talk. So it's more a talk which is aimed to younger students. And my main purpose will be to show some ideas, which are related to log-Sobolev inequalities. So I will start with a brief introduction of the main character, of the talk today, which is log-Sobolev inequality in Rn for the Gaussian measure. So the basic statement of the inequality is the following. If you consider the Gaussian measure on Rn, which is centered and variance 1, then it's possible to control the entropy of any function in terms of the energy of the function. So the statement of the inequality is the following. You are able to bound the entropy of f squared with respect to the Gaussian measure in terms of the total energy of the function, which I defined as being the integral over Rn of the norm of the gradient. So some first brief historical perspective on the study of this inequality. The inequality involves, on the left-hand side, the entropy of the function f squared, which is a notion, that has been studied for a very long time, that first appeared in mathematical physics and was particularly important in the works by Boltzmann in the 19th century. So you can see Boltzmann on the left picture. And was kind of rediscovered in another framework by Shannon in the context of information theory. So Shannon is the picture on the right-hand side. So log-Sobolev inequality in themselves appeared before the famous paper by Lengroth, and can be seen in different forms under different names in works by Stam, in information theory, in a work by Federbush in mathematical physics. However, log-Sobolev inequality became the central object of studies in a very famous paper by Lengroth in 1975, where the importance of this inequality was illustrated clearly in connection with hypercontractivity properties and regularization properties of semigroup. In particular, in this paper by Lengroth, the equivalence between the log-Sobolev inequality for the Gaussian measure, as I presented it on the first slide, and the hypercontractivity of the Ornstein-Uhlenbeck semigroup that was put forward earlier in papers by Ed Nelson in 1966 and 1967, is shown in the paper by Lengroth. That is, he established in a clear way the equivalence between the log-Sobolev inequality and the hypercontractivity property of the Ornstein-Uhlenbeck semigroup. So a very quick comment about the inequality in itself. If you look at it from the analytic point of view, that is assuming that you come from analysis, this inequality belongs to the large family of Sobolev type inequalities. It provides an improvement of integrability. So a very naive way to look at it is you have a function which is in L2 of the Gaussian measure, whose gradient is also in L2, then actually the function is more than in L2. It's such that f square root of log f is also in L2. So this is the typical feature of the Sobolev inequality. If you have a function which is in some LP, you know also some integrability property of its derivative. You have for free an improvement of the integrability of the function, which is quantified extremely precisely by a Sobolev inequality. So this log-Sobolev inequality belongs to this family of Sobolev inequalities. Something which is striking about the log-Sobolev inequality is that you see that on the right-hand side, in front of the energy of the function, I have the constant 2. So this is very striking that this constant 2 is the same for all the An. And in particular, the constant is optimal, that is the extremals in the log-Sobolev inequality are easily seen to be the exponential functions. The fact that this constant 2 is independent of the dimension is illustrative of the fact that actually log-Sobolev inequalities are inequalities that are going to hold, unlike the Sobolev one, in infinite dimensions. So this is an aspect of the log-Sobolev inequality I will be trying to illustrate a little later in the talk. So there exist numerous proofs of this inequality. Once Michel Ledoux shared to me that he knew 15 proofs of log-Sobolev, so I don't know as many proofs. I will try to give you 3 proofs, which are different, and each of them can be generalized in different directions. So as this is often the case in mathematics, when you have a theorem or a statement that you like, it's always useful, to think about different proofs of this statement, because different proofs, shed different light on the phenomenon of the theorem or the statement, and they can be generalized in different directions. So the first proof, which is amazing, is a proof by Lengross, which is based on the observation that the log-Sobolev inequality is an inequality which is stable by tensorization. So essentially, proving the log-Sobolev inequality for the Gaussian measure will follow from the log-Sobolev inequality on a 2-point space for a Bernoulli random variable. Then, using tensorization and central limit theorem, you get the log-Sobolev inequality for the Gaussian measure as a consequence of the log-Sobolev inequality on a 2-point space. And the optimal constant 2 is preserved by the tensorization process. So even though this proof is amazing, I will not present it to you. I've decided for my talk to focus on the semi-group approach to the log-Sobolev inequalities. So a proof that we are going to see together in the next few slides that has been discovered by Bakri and Emry is the so-called Ornstein-Uhlenbeck semi-group interpolation proof, where the idea is to look at the entropy functional along the Ornstein-Uhlenbeck semi-group and study some monotonicity property of this entropy functional. So with a second proof that I will develop during the talk. This is a proof based on stochastic calculus, which is presumably due to Jacques Neveu, where log-Sobolev inequality for the Gaussian measure is simply seen as a consequence of an inequality that holds on the space of Brownian functional, that is, of an inequality that holds on the Wiener space. Then the log-Sobolev inequality for the Gaussian measure is just a finite dimensional trace of these inequalities that lives on the Wiener space. The third proof, and the fourth that I mentioned today, the third proof I want to develop will be the heat kernel measure approach that has been first devised by Bakri and Ledoux and that has been pushed forward by Driver and Hu and applied in the context of loop groups by Driver, which is an interpolation ID, again, of the entropy functional along the semigroup, but this time not the Ornstein-Uhlenbeck semigroup, but the heat semigroup itself. So the first proof, which is based on interpolation along the Einstein-Uhlenbeck semigroup. So the idea is to consider first the Einstein-Uhlenbeck operator on Rn, which is defined as the Laplacian minus x inner product with a gradient, and note as a starting point that C's diffusion operator admits the Gaussian random variable, the Gaussian distribution gamma, as an invariant and symmetric measure. So representation for the semigroup, the Einstein-Uhlenbeck semigroup is well known and is given by the Meller's formula. This is a Gaussian semigroup for which the mean and the variance can be computed, leading then to the representation of the semigroup of the Einstein-Uhlenbeck. So based on this very nice formula, this is straightforward to observe a commutation between the gradient and the Einstein-Uhlenbeck semigroup. More precisely, if you look at the formula for Pt, which is given by the Meller's formula, if you differentiate Pt with respect to x, you see immediately that the gradient of Pt is equal exactly to exponential minus t Pt of the gradient. This is a typical commutation property between the first order derivative and the semigroup. So the Meller formula, not only does it give this commutation property between the gradient and the semigroup, it also automatically implies, or at least we can see immediately from it, that it implies a convergence to equilibrium at an exponential rate when t goes to infinity. So more precisely, when t goes to infinity, Pt of f is going to converge to an equilibrium, which is the average of f with respect to the invariant measure, which is in this case the Gaussian distribution, the Gaussian measure. So based on these two observations, we have the two ingredients we need to prove the log-Sobolev inequality using this interpolation technique. So before going to the proof itself, there is something I would like to mention, because this is actually at the core of the argument. This is a subcommutation between the semigroup and the gradient. This subcommutation is actually enough to run the argument instead of the commutation itself. So the commutation for the Einstein-Uhlenbeck semigroup immediately implies, using triangle inequality, of course, that it's possible to control the norm of the gradient in terms of Pt of the gradient. So this is again a regularization property for the semigroup Pt, which is quantified in terms of this subcommutation property. So let's now go to the heart of the proof of the gross log-Sobolev inequality using interpolation along the Einstein-Uhlenbeck semigroup. So the basic idea will be to see the entropy of F as being the total variation of the entropy of PTF when t goes from 0 to plus infinity. So simply by writing that when t is equal to 0, PTF log PTF is equal to f log f, and then when t is equal to infinity, PTF log PTF is the integral of f times the log of the integral of f. Okay, this is the interpolation formula. Then you just write that the variation of the entropy is the integral of the derivative. And then you start doing calculus with the integral of the derivative. That is, if you differentiate with respect to time the expression PTF log of PTF, and use the fact that PTF, by definition, is a solution of the heat equation. In other words, that the derivative of PTF with respect to T is equal to L of PTF, you see immediately that the entropy of the function f can also be written as an integral of LPT log of PTF. Observe that if you apply the chain rule, you would have another term that would be L of PTF divided by PTF times PTF. But this is the same as the integral of L of PTF. And I remind you that the integral of L of PTF has to be equal to 0 because gamma is an invariant measure for the semigroup Pt. Then, after applying chain rule, you integrate by part. Okay, that is the idea would be to transform a second-order derivative into a first-order derivative using integration by part. So if you use the integration by part for the Laplace operator in Rn, you'll see that the integral of LPTF L times the log of PTF is nothing else but the norm of the grad of PTF squared that you divide by PTF. Now is the time to use my ingredients. So far, I only did calculus. I did not use any specific property of the semigroup, besides the fact that I have convergence to equilibrium when t goes to infinity. So the key point is now to use the subcommutation property between the gradient and the semigroup that I was trying to stress a few slides ago. So using this subcommutation, you are going to bound the gradient of the semigroup by exponential minus 2t pt of the gradient squared. And in the next step, you use Cauchy-Schwarz inequality to make the energy of F appear. Using Cauchy-Schwarz inequality and using the fact that it-kernel measures, are probability measures, this is easy to see that you can control pt of gradient of f in terms of PTF, pt of the grad f squared divided by f. You just write the norm of the gradient is the same as the norm of the gradient divided by square root of f times square root of f. And then you use Cauchy-Schwarz inequality with respect to the heat-kernel measure of the Einstein-Uhlenbeck semigroup. So coming back to the interpolation argument, what you got so far is the entropy of the function f can be controlled in terms of this quantity on the right-hand side that involves the Fisher information of f. So now is the time to obtain the log-Sobolev inequality using the fact that the integral of pt with respect to gamma is a function itself, that is, gamma is an invariant measure, and using the fact that the integral from 0 to plus infinity of exponential minus 2t is equal to 1/2, you end up, after doing your interpolation, with the inequality, which is the desired inequality. The entropy of f can be controlled in terms of the Fisher information. Now, if you prefer to deal with the energy form of the log-Sobolev inequality, this is enough to replace f by f squared to obtain the inequality with the constant 2 that I gave to you and the energy of f on the right-hand side. So what we used in this proof are basically, the interpolation property along the semigroup pt together with the subcommutation property of pt. This is the main ingredient. So another point, maybe a remark, is that the sharp constant 2 in the log-Sobolev inequality in this proof appears as the integral from 0 to plus infinity of the exponential minus 2t dt. The second proof I would like to stress, and later generalized in different framework, is the Clark-Ocon formula approach. That is, if you prefer dealing with stochastic calculus rather than semigroup theory, you have a proof for you, which is based on the Brownian motion. So consider Bt to be an n-dimensional Brownian motion, and Clark-Ocon formula is a formula which is a representation formula for functionals of this Brownian motion. So what the Clark-Ocon formula gives is an explicit representation of the integrand in the Ito representation formula for martingales. So it's possible to write any Brownian functional big F as a stochastic integral with respect to the Brownian motion B in terms of the so-called Malyavin derivative on the Wiener space. So Malyavin derivative is an object on which I will come back a little later in the talk. It's a derivative which is defined for functional of the Brownian motion. So you can think of it, very naively speaking, as a Frechet derivative on the space of Brownian functions. So this Clark-Oakland formula, a way to prove it, is using the integration by parts formula, which is at the basis of Maillard-Van calculus. So Clark-Oakland formula, and this is something that I'm going to use a little later, is a very straightforward consequence formula of the integration by parts formula on the path space. So the statement of Clark-Oakland formula tells us that if you look at the martingale exponential of f given bt, where bt is the natural filtration of the Brownian motion B, then the representation of the stochastic derivative of mt, that is the integrand, is given exactly in terms of the Maillard-Van derivative of the functional f, where I forgot to write the conditional expectation. So there is a typo at the bottom of the page. It should be conditional expectation of dtf given bt. So now that you have a representation of the stochastic derivative of the martingale mt, you can play around with Ito calculus. In particular, if you want to study the entropy functional, this is a good idea to try to apply Ito's formula to mt log mt. So using Ito's formula for mt log mt, where mt is a martingale that I introduced before, and taking expectation, assuming that the local martingale part has an expectation that vanishes, you end up with the following representation of expectation of m1 log of m1 minus expectation of m0 log of m0 in terms of the quadratic variation of the semi-martingale mt log of mt. So the computation of the quadratic variation in Ito's formula for mt log of mt yields this 1/2 of expectation of integral from 0 to 1 of 1 over ms square, the norm square of the conditional expectation of the Maillard-Van derivative. Therefore, coming back to the definition of the martingale mt, I remind you that mt is a conditional expectation of f given bt. At time 1, this martingale is f, the random variable I am interested in. And at time 0, this is simply the expectation of f. So we get that the entropy of the random variable f can be written in terms of the Maillard-Van derivative. In particular, this is equal to 1/2 the expectation of the integral from 0 to 1 of this expression which is inside of the integral. That already looks like a Fisher information on the Wiener space. So now the next step will be to use Cauchy-Schwarz inequality and replacing f by f squared. So if you replace f by f squared in the previous equality that I obtained, and you use Cauchy-Schwarz inequality after applying chain rule for the Maillard-Van derivative, you are able to control the norm of the conditional expectation of the Maillard-Van derivative of f squared in terms of the conditional expectation of f squared itself and the conditional expectation of the norm of the Maillard-Van derivative. So the conditional expectation of f squared simplify, and I end up, after applying the fact that the conditional expectation is a contraction in L2, I end up with the fact that the entropy of the random variable f squared can be bounded from above by 2 times the integral from 0 to 1 of the total energy of f, of the random variable f. So this is the log-Sobolev inequality on the Wiener space. A very special case of this log-Sobolev inequality, which holds, you should note, with the same optimal constant 2, which is dimension independent, as I already stressed out. A very special case is given where you take, for the functional of the Brownian motion, the endpoint. That is, if you apply the log-Sobolev inequality on the Wiener space to the functional f is a function of b1, and you observe that b1 is nothing else but distributed as a Gaussian random variable in Rn with mean 0 and variance 1, you get the log-Sobolev inequality with the optimal constant 2. So what I like in this proof is that this proof illustrates the fact that the log-Sobolev inequality in An can be seen as a trace, a finite dimensional trace of an infinite dimensional log-Sobolev inequality that holds on the path space. The third proof I would like to stress is based on the heat kernel measure approach. So in this proof, we are going to see the Gaussian random variable with mean 0 and variance 1 as being simply the heat kernel at time 1 issued from 0, heat kernel being the Euclidean heat kernel. So if you consider the heat semigroup, the Euclidean heat semigroup, which is simply the semigroup generated by the Laplacian An, which is given explicitly as a convolution with the Gaussian kernel, the density of this heat semigroup at time 1, if you plug in x is equal to 0, is the Gaussian measure gamma. So then you are going to perform an interpolation along an interpolation of the entropy functional along this heat semigroup, but not from 0 to plus infinity as you did for the Einstein semigroup, but an interpolation between 0 and 1. So evaluating the variation of the entropy, we can write, as we did before for the Einstein-Uhlenbeck semigroup, the entropy of the semigroup at time 1, that is P1 of f log f minus P1f log of P1f, can be written as the integral from 0 to 1 of the derivative of this forward-backward functional of the heat semigroup, which is given in my slides. This is the same observation as before, is that when S is equal to 0, you know this forward-backward interpolation of the semigroup is nothing else than P1 f log of P1f, and the value when S is equal to 1 is P1 of egg log f times log f. So writing that the variation is equal to the integral of the derivative, and then differentiating the expression, that is, if you differentiate with respect to S, the forward-backward interpolation, and you use chain rule, you know, together with the fact that P solves the heat equation with respect to the Laplacian, you get a very nice formula, which is extremely clean. That is, there are a lot of terms that simplify. Then when you apply chain rule, I did not write them explicitly, but you have explicitly a formula, you know, for this derivative of the forward-backward interpolation in terms of the PS of P1 minus f of the norm of the gradient of P1 minus f squared. The next observation is that we need to go at order 2 to study the monotonicity property of the forward-backward functional. And if you differentiate one more time this quantity which is inside of the integral, you will see that this is increasing. That is, the derivative with respect to S of this forward-backward interpolation is actually non-negative all the time. There is an explicit formula which is given in terms of the Hessian of the log of P1 minus SF squared. So what we are using hidden in the argument is a convexity property of the entropy functional along the heat semigroup flow. So using this monotonicity property of the functional, we bound simply, you know, the term in the integral by the largest value, which is obtained when S is equal to 1. If you bound the value by S is equal to 1, you get immediately that the entropy of the function f can be controlled by P1 of f, the norm of the gradient of log f squared, which is the Fisher information of f. This is immediately the sharp log-Sobolev inequality when you replace, as you did before, you know, f by f squared, and you get from this proof, that is by interpolation and using the convexity property of the entropy functional along the heat semigroup flow, you get the sharp log-Sobolev inequality for the heat kernel measure of the heat semigroup, which is nothing else but the Gaussian measure. So these are the three proofs of the log-Sobolev inequality I wanted to point out in this talk, because I'm going to try to generalize them in different directions to see where they can be generalized. Okay, so more generally, a log-Sobolev inequality can be stated in an abstract form, for instance, in the context of a Dirichlet space. A log-Sobolev inequality on a Dirichlet space is an inequality that relates the entropy of a function f to the energy of this function f. So the type of log-Sobolev inequality we are going to be interested in are log-Sobolev inequality where the entropy of the function f squared is bounded from above by a constant that on purpose I write in the form of 2 over rho times the integral of gamma of f d mu. So the integral of gamma of f d mu in the sequel is going to be a Dirichlet form. You should think of it as being a generalized energy of the function f on an abstract space. So for instance, if you want to put the explicit examples that we have been studying at the beginning of the talk into this framework, what we already proved is that the log-Sobolev inequality is true on the space X, which is equal to Rn, equipped with a measure mu, which is a Gaussian measure, and where the Dirichlet form of interest is the energy form with respect to the Gaussian measure. So log-Sobolev inequality are at the intersection of many areas of mathematics, and this is maybe why they admit so many proofs. And the field of application of this inequality is still growing nowadays. That is, they were extensively studied starting from 1975, and the field of application is still expanding today. So I cannot, of course, mention all of the application, but I will just mention some directions that are particularly active. So first set of directions that has been following the study of log-Sobolev is a study of isoperimetric inequality in infinite dimension and related concentration inequality. So this line of research was particularly developed around works by Ledoux, Talagrand, Moudray, and Bobkov. There is line of research about applications of log-Sobolev inequality to Riemannian geometry, to sub-Riemannian geometry, to analysis in infinite dimensional spaces, because one of the features of this inequality, as I told you, is that they hold in infinite dimension, because the optimal constant in those inequalities are independent of the dimensions. They found application in statistical mechanics, analysis on metric measure spaces more recently, where log-Sobolev inequalities actually can be taken as definition of curvature bounds on rough metric spaces. They have been applied recently to prove convergence to equilibrium for solutions of PDE. So they found application in PDE theory and to the study of heat kernel bounds. So I do not pretend to be exhaustive, but I just wanted to point out some of the areas in which log-Sobolev inequality can be used. So in that general setting of Dirichlet space, I would like to mention a general theorem, which is a fundamental theorem by Lengroth, which relates the log-Sobolev inequality, which is stated in this abstract framework of a Dirichlet space, to a regularization property of the semigroup associated with this Dirichlet space. That is essentially what says the log-Sobolev inequality. This is a property about the improvement of integrability for the semigroup PT. So this is a regularization property of the semigroup PT. So the following properties are equivalent in the framework of Dirichlet spaces. The log-Sobolev inequality holds with this constant 2 over rho, if and only if there is an entropy decay of the semigroup itself. That is, the semigroup PT is going to converge to equilibrium to the invariant measure mu in the entropy distance. That is with respect to the entropy. And the third property is called the hypercontractivity property of the semigroup. It says that the semigroup improves the integrability of the function f when the time t is large enough. So this is a regularization property saying that a function f in LP is transformed into a function f in LQ by the semigroup when T is large enough. So let me now play around with the proof that I gave you, the three proofs of the log-Sobolev inequality. I will try to play with them and to see in which direction they can be generalized. So the first proof I mentioned is a proof by interpolation along the Einstein-Uhlenbeck semigroup. So I'm going to try to generalize this proof in a framework, for instance, of a Riemannian manifold equipped with a weight measure, which is going to be an exponential density with respect to the volume measure. And the log-Sobolev inequality I'm going to be interested in is a control of the entropy of the function f squared on this Riemannian manifold in terms of an energy form, which is given by the gradient associated with the Riemannian structure, and a measure, which is this weight measure I've been considering. So the basic question I will be asking is that under which condition on the geometry of the manifold M and analytic property of the weight U can I run the Einstein-Uhlenbeck interpolation method to get a proof of the log-Sobolev inequality. So as you have seen, we need two ingredients to run the Einstein-Uhlenbeck interpolation method. The first ingredient is that we need an Einstein-Uhlenbeck operator. So in that framework, the Einstein-Uhlenbeck operator is going to be the generator of the Dirichlet form I am interested in. This is simply the operator which is given by the Laplacian minus the gradient of the weight. So this operator satisfies the property I've been using in my proof of the Gaussian log-Sobolev inequality using the Einstein-Uhlenbeck interpolation. It admits my weighted measure as an invariant and symmetric measure. And the second ingredient I need is the subcommutation property for the semigroup. So this is where the geometry is going to enter into the play. It's possible to prove that this subcommutation property for the semigroup turns out to be equivalent to the non-negativity of a tensor, which is associated both to the geometry of the manifold in the term of the Ricci curvature, and it's going to be associated with the convexity property of the weight I've been using on my manifold in terms of the Hessian of U. So the subcommutation ingredient that I've been using in my Einstein-Uhlenbeck interpolation proof is made available in that geometric framework as long as I am able to control from below this tensor, which is called, by the way, the Bakry-Emery tensor of the Riemannian, of the weighted Riemannian manifold. So this subcommutation is satisfied if and only if this tensor is bounded from below by the constant rho. As a consequence of this result that relates the subcommutation to a lower bound on this tensor Ric plus Hessian, using exactly the same proof as I did in the Gaussian case, I obtained without any further work the log-Sobolev inequality on weighted Riemannian manifold. This is exactly the same proof. So the conclusion is that we just need the subcommutation to run the Einstein-Uhlenbeck interpolation technique. So Bakry-Emery criterion is a way to generalize in an abstract framework this method. That is, the Bakry-Emery calculus is tailor-made to run the Einstein-Uhlenbeck interpolation method in an abstract framework. So consider a general diffusion operator that could be on a manifold or on a more general Dirichlet space, actually, which is symmetric with respect to a measure mu. We can compute an analog of this Bakry-Emery tensor in the form of a gamma-2 operator, which is an object which is constructed intrinsically from the operator L. The idea of the Bakry-Emery calculus, the gamma-2 calculus, is to extract from L an intrinsic notion of curvature that will allow you to perform the Einstein-Uhlenbeck interpolation method to prove the log-Sobolev inequality. So the first idea is to extract from L a generalized notion of gradient, which is obtained by the so-called carré du champ operator that was first introduced by Paul-André Meyer, and iterates its definition, as was done by Dominique Bacri, to get the so-called gamma-2 operator, which is going to play the role of the intrinsic curvature of the operator L. So for instance, if you perform this calculus on Rn, where delta is the Laplacian, the carré du champ operator is nothing else but the gradient, the bilinear form given by the gradient, and the gamma-2 operator is the Hilbert-Schmidt norm of the Hessian. So what is the Bacri-Henry criterion? Bacri-Henry criterion is a lower bound of gamma-2 in terms of gamma. So we are going to say that the operator L satisfies the Bacri-Henry criterion with parameter rho if and only if it's possible to bound from below gamma-2 by rho. So example, if you apply the gamma-2 calculus to the case of the Einstein-Uhlenbeck operator on a weighted space, the Bacri-Henry criterion is equivalent to the uniform convexity of the potential. So other typical examples that have already been pointed out, this is a case of Laplacian operator on Riemannian manifold. I will go a little bit quicker here because I would like to present the end of my talk. So Bacri-Henry criterion is actually exactly what we need for the subcommutation ingredient. So it turns out that this is exactly equivalent to the subcommutation property I've been trying to stress out from the very beginning. That is, the subcommutation property for the semigroup is equivalent to the validity of the Bacri-Henry criterion. This is abstract framework. So you see now where the statement on the weighted Riemannian manifold came from. The subcommutation property for the semigroup on a weighted Riemannian manifold was equivalent to a lower bound on the Bacri-Henry tensor because of this Bacri-Henry criterion that was in the background. So if we put the pieces together and we apply exactly the same proof that we did in the case of Rn, we conclude that at a high level of generality, this is enough to get the Bacri-Henry criterion with the parameter rho to get the log-Sobolev inequality with a constant 2 over rho. Again, the proof is exactly the same as for the proof of the log-Sobolev inequality that relied upon the Einstein-Uhlenbeck interpolation method. So this was playing around with my proof number 1 of the log-Sobolev inequality. At this level of generality, we may wonder what does the approach number 3 gives, which was the approach by the heat kernel measure. And it turns out that in this context of semigroup or diffusion operator satisfying the Bacri-Henry criterion, if you mimic the heat kernel measure proof of the log-Sobolev inequality in Rn, that is, you apply the convexity property of the entropy functional along the heat semigroup flow, you get something which is stronger than what we did before, that we obtained before. So playing around with the proof number 3 gives us a stronger statement, which is going to be a family of log-Sobolev inequality depending on time. That is, the heat kernel measure approach to the log-Sobolev inequality yields that for any diffusion that satisfies the Bacri-Henry criterion, there is a log-Sobolev inequality with a constant which is explicit. The constant is 1 minus exponential minus 2 rho t divided by 2 rho for any t. So in particular, and this is actually a very special case, if rho is positive, by letting t goes to infinity, we recover the log-Sobolev inequality for the invariant measure of the semigroup Pt. So this family of log-Sobolev inequalities that depend on time for the heat kernel measure allow to recover, when t goes to infinity, the log-Sobolev inequality for the invariant measure mu itself. So this is actually a stronger form than the Einstein-Uhlenbeck interpolation method. So this type of approach to log-Sobolev inequality for the heat kernel measure was further developed, in particular in infinite dimension in works by Driver and Lorentz. And this type of techniques were applied, for instance, in the context of pinned loop groups. So now, maybe to conclude, let me play around with my proof number 2 of the log-Sobolev inequality that was based on the Clark-Ohlson formula. And let me apply the method of the proof in a Riemannian setting. So I'm going to follow the approach by Capitaine Chou and Ledoux to prove a log-Sobolev inequality on a path space over a Riemannian manifold whose trace, could yield the log-Sobolev inequality for the heat kernel measure on the Riemannian manifold. So as you have seen, and this is something I tried to stress from the very beginning, the starting point is a Clark-Ohlson formula, which is based on the integration by parts formula. So the tool which is required to run the method and to run this proof number 2 is the integration by parts formula on the path space. So fortunately, there has been a remarkable paper by Bruce in 1992, where he proved the integration by parts formula on the path space over a Riemannian manifold, therefore opening the door to Malia-Van calculus on pi spaces over Riemannian manifold, and in particular to the proof of the log-Sobolev inequality following the Neveu method. So in a nutshell, so I don't want to enter into the details here because I'm pretty sure that Elton is going to speak more about it tomorrow. So in a nutshell, the approach is the following. We first have a Malia-Van derivative on the path space over a Riemannian manifold that, very loosely speaking, I can define as follows. The main idea is that you have a Brownian motion on a Riemannian manifold that you start from a point X. You can construct a Brownian motion on a tangent space by using parallel transport along the path of the Brownian motion of the manifold. Then, associated to this parallel transport and this Brownian motion in the Euclidean space, which is in the background, we can define the damped Malia-Van derivative that takes into account the curvature of the manifold. So the damped Malia-Van derivative is defined as a modified version of the Malia-Van derivative using the curvature of the manifold, the Ricci curvature, and the integration by parts formula that holds on the path space is written in terms of this damped Malia-Van derivative. That is, any functional of the Brownian motion on the Riemannian manifold can be integrated by parts in terms of this damped Malia-Van derivative. So this integration by parts formula yields, the Clark-Ohlson formula, which is the only ingredient we need to apply the log-Sobolev, to apply the log-Sobolev proof that I gave you using the Clark-Ohlson formula. So in particular, we get a log-Sobolev inequality on the Riemannian path space that Elton is going to, I think, to develop into more details. So I only focused on 3 proofs, for the log-Sobolev inequality that I try to generalize in several directions. But you can try to play the same games, with the other proof of the log-Sobolev inequality that for instance, the proof based on sharp Sobolev embeddings, proof based on direct hypercontractivity proof for the Einstein-Uhlenbeck semigroup, and try to generalize them in different ways. And you are going to get an interesting mathematical adventure trying to generalize the proof in different settings, showing hence, that log-Sobolev inequality turns out to be at the center, of a circle of ideas, reaching far out of the original aim. So this is it for today. Essentially, this is all what I wanted to say. Thank you very much.
Thank you, Fabrice, for that excellent talk. Let's thank Fabrice. And so now, if anyone has